just the lights, because I don't think it's going to.
Yeah. Okay, got this one.
Heat treatment. Are there questions on anything else we've covered in class so far? So the heat treatment should actually dovetail pretty well with the things that you.
And was hopefully here what we'll get into is a bit more in-depth physical metallurgy of what's going on in the treatment. And I included several references here that I find very helpful. I use in terms of I think they do a very nice job with respect to the heat treatment of steel, and would encourage you to all take a look at them and perhaps acquire your own. A lot of them are older, out-of-print references, which means they're actually really cheap compared to your current textbooks. Do you even use textbooks anymore? You guys still have textbooks? Okay. Like my kids and my daughter's in high school, and I never see her with a textbook. Really, it's just all on the tablet or the iPad or whatever. So, anyway, they're great references. So, we've got a breakdown of what we'll cover. It's a pretty kind of pretty in-depth section of the class, and there's no way we can get through it all in one day. There is a lot of material here, and I would encourage you, as always, to ask questions so that we don't go past anything too quickly. So the strength of iron is based on heating and cooling. Why? Why does that work? We know this. We practiced it already, but why does it work?
Magic. Different microstructures and atomic cooling range.
Well, that's true, but why?
Oh, because it has to do with the fusion of carbon.
Okay, yeah, carbon, yeah, Raphael?
I was just going to say the different crystal structures have different properties, so some can be harder than other ones, specified steel rule.
Okay, that's true, but why can we get different crystal structures? Why is that possible? I've stumped the whole class again. Yes, Alex.
Does it just have to do with solubility of all the solutes?
Right. It's related to the atomic radius of iron and carbon, right? Iron and carbon being so much smaller, that gives it the ability to be, does anyone remember the proper term for that? What type of an alloying element we call that? Because it's really small, what does it do?
Interstitial.
That's right, it's interstitial. And the alternate type would be? Substitutional, right? And that's based on the size of the atomic radius of the element that you're discussing. Carbon in particular, being very small, allows it to have occupy those interstitial sites. And iron, even without carbon, would go through a phase change, right? That's what Raphael was talking about. It's going to go through a phase change. So we combine the two together, iron's tendency to go through phase change, carbon's very small atomic radius, and then now we can start to develop the different microstructures. There's the schematic representation of those things. And we call, well, just as a review, we have, when we go from a liquid to two solids, we call that a eutectic reaction. We see that on the phase diagram. Of course, in our class, we've not dealt with that. If you've taken a casting class, you certainly would. But what we do deal with is the eutectoid reaction, which is one solid going to two new solids, right? And that's what's happening when we go through, for example, austenite, solid number 1, to ferrite and iron carbide, which is what you get when you cool a piece of steel down, right? So austenite is what we have at the higher temperatures. And we can see a bit what that looks like. And austenite has an FCC crystal structure. I hope this is all review. If it's not, and you need me to slow down, I will. Ferrite, of course, has the BCC crystal structure, and on our little equation, it's over here. And you can see what ferrite looks like. And then iron carbide, which is, of course, a combination. It's Fe3C rather than a pure element. It's a this has got 6.6% carbon, right, in this orthorhombic crystal structure. And again, it's the last component of our eutectoid reaction. We see it most often as a constituent of pearlite, right? And we would all, I hope, agree that pearlite is not a phase. It's a combination of two different things, right? It's a combination of ferrite, the white stripes, and iron carbide, the gray stripes. So that's one way that we see iron carbide or cementite represented. We will see that it can show up in other ways with other appearances depending on what we're doing. Martensite, which does not form by diffusion but rather by shear, is locking that iron carbide into a different crystal structure. And that's why we get such high hardness, because it's an unstable material. The carbon would, or iron carbide would really like to get out, but it's trapped and stuck, and it exerts a significant strain on the microstructure, and thereby increasing the hardness and changing the properties quite dramatically from what you'd otherwise have.
One of the ways I explain it is it messes with the slip planes,
Sure.
because it distorts the slip planes, and now we can't have slip because they're uneven.
Mm-hmm. You look like you have a question. No? Okay. All right. So in this case, for the martensitic transformation, it's happening very quickly. There isn't time for diffusion to occur, and so we get that locking effect. So what I want to do is take you through a series of experiments that other researchers have done. These were done by a fellow named M.A. Grossman. I'm not sure if I mentioned him before. Did I talk about him in class already? M.A. Grossman. So he was an early metallurgical researcher and the author of one of the references that I had up there at the beginning of class. He was named after a guy named Marcus Aurelius, who was Roman or Greek? I can't remember. But if you ever saw the movie The Gladiator, that character shows up in there. So that's kind of how I remember his name. Anyway, he did a series of experiments where he started with plain carbon steels that had just carbon and really nothing else for alloying, different amounts of carbon, and he executed a variety of different heat treatments just to see what would happen. And so what I've done is I've copied from his book the microstructures and the heat treatments that he used, so we can see what he got. And if you get a chance to look at his book in person, you'll see that the microstructures are actually even better. These are photocopies, so they're marginal, but if you see the book, they actually are very, very clear structures. I think I'm actually quite impressive for not having the digital microscopy, the tools that we have today. So what he did, he started with in this case, a 43 carbon steel, and this is what it looked like, the structure that it had in the as received condition. We see here the magnification of 100x, and over there 1000x. We can see we have ferrite and we have pearlite. And that's the expected structure for a slowly cooled 43 carbon material. Notice that in doing a hardness test, he reported this as 10 Rockwell C. Also note that that's not actually a valid Rockwell C number. You got to be at least 20. So today we would report that as Rockwell B or as Brinell or some other hardness scale. The point is that it's very soft. So he takes that piece of steel and he heats it up to 1320 degrees Fahrenheit. And he quenches it. And in doing that, he gets a change in the microstructure. And he's identified that here, this M, as some martensite. And here we have some ferrite. And he has also still quite a lot of pearlite. He then repeats the experiment, but heats the metal up to 1340. And again, we see a change in the microstructure. Still a mix of pearlite, ferrite, and martensite, but different amounts of each. We also see that the hardness is increasing. So initially we started with what he called a Rockwell C of 10. Here we're at 19, still not really quite a valid number. And then he's up to 27. And let's see, I feel like I jumped way too much. Nope, okay. So then he continues increasing the austenitizing temperature to 1380 and then subsequently to 1425, quenching looking at the microstructure, and we see that as he progresses, his microstructures are changing dramatically. We have much more martensite now. We still have some ferrite, but very little pearlite, and the same kind of thing over there. And we see we're continuing to increase the hardness. And he continued to do this all the way up to, this one here is 1450. He went up to 1550, and then he slowly cooled this to 1325 and then quenched it, just to see what would happen. And what he found was that when he just did a 1450 austatize and quench, he got Rockwell 60. When he heated even higher and then came back down a little bit and then quenched, he started to see the hardness drop off just a little bit. He continued the experiment of heating up to 1550 and then allowing things to slowly cool to lower and lower temperatures. And what we see is that the microstructure is still mostly martensite, but changing a bit, and the hardness is continuing to decrease. And here he allowed it to go down to 1225 and then all the way down to 1200. And you can see now we're back to some of the hardness values that we saw earlier in the experiment when he was kind of going on the way up in terms of temperature. And from the microstructural standpoint, this is pretty similar to what he started with. So that was quite interesting, but that was only one composition. That's a 0.43 carbon. So if we plot what he did, or not plot, but just show, summarize it, we see that from just this one set of experiments, he determined that there's some minimum temperature below which no changes will occur. That's to say, if you heat to 1100 degrees and quench, you're not going to get any changes in the structure or the hardness. You have to get over some minimum point to get any change, and he was able to establish what that was. And then if he continues to increase the temperature, he will get increasing hardness. If he heats from 1300 to 1350 to 1400 and quench from those increasing temperatures, he gets a change in structure and an increase in hardness. Yeah, Raphael.
Which phases are present with the lower hardness values typically? Or is like they're kind of like a specific kind of base?
So in the very lowest hardness, we saw a combination of ferrite and pearlite. In some of the other steps, he had varying amounts of martensite, ferrite, and pearlite. When he got to having all, sort of the max hardness that he could get, which in that case was a 60, there was no ferrite present. There was no pearlite present. You saw essentially a uniformly martensitic structure. So the structure is changing depending on where he's at in terms of temperature. When what's the temperature he's quenching from makes a difference into what his outcome is.
Yeah, and then from your explanation of pearlite being not necessarily a phase, but rather the presence of two different phases.
Yes.
When you say that there was a combination of pearlite and ferrite, does the pearlite, is it still?
So pearlite is always ferrite and iron carbide in a lamellar structure, lamellar arrangement. That's the definition of pearlite. You can have ferrite as just a standalone structure. We would often refer to it as blocky ferrite. So you can have pearlite and ferrite both present, pearlite being a combination of two things and ferrite just being basically pure iron.
It's very confusing. I have a lot of trouble explaining this to my students too. But think about pearlite is a naturally occurring composite of ferrite and cementite, and the way it arranges itself, the average composition is about 0.8%. And then that can group, that always groups together like that, and then you have areas where you don't have enough carbon where ferrite will be present.
Right. Yep.
So.
Okay. Any other questions before we keep going?
One other point on that is that the hardness of pearlite is also determined not only by the fact that it's there or not, but how far apart the little plates are. The finer they are, that composite acts a little bit harder.
Yeah, you can actually make pearlite very hard if you process it correctly. And railroad rails are about a 1080 in terms of composition. And they have a hardness slightly over 400 Brunel, which is going to be roughly 40-ish Rockwell C. and they're fully pearlitic. They intentionally keep martensite out because if they formed a martensite, it would lead to premature failure of the rail. The rail, if you think about the rail, it's got the train wheel rolling across it. So you have, much like you would have in a bearing, a ball bearing or a roller bearing, you have what they call rolling contact fatigue. And if you had martensite present, that's actually going to be an extra hard particle that's going to lead to premature spalling of the rail surface. So when they manufacture them, they're actually heat treated to generate a pearlitic structure, but with a very fine layer spacing, so they get the higher hardness, but good toughness. A few other conclusions. There's a temperature above which heating and no changes happen, right? We saw that at 1450 when he quenched, he got Rockwell 60. When he went all the way up to 1550, he did do some slow cooling after that, but he didn't get any higher hardness, right? He kind of topped out. He could have, and he didn't do this, but he could have gone up to 1600 and he still wouldn't have gotten any different response. And then reducing the temperature below some specific temperature prior to quenching will result in a decrease in hardness from the maximum potential hardness. So that was the second half of his experiment. We see this over here. Heats to 1550 and we slow cool to varying temperatures, and we see that we're getting decreases in hardness as we go to lower and lower temperatures before we quench. And we also saw that there was microstructural changes that went along with that. Okay. Any questions before I move away from this? Okay, so now he does a similar set of experiments, but this time he uses a 0.13 carbon, so much lower carbon. And again, we have what the structure is in the as received condition, both at 100x and 1000x. We see here there is some pearlite. In this image, it looks almost black, but if you had enough magnification, you'd see it still has a layer arrangement to it. It's just very, very fine. But all the rest of this is ferrite. So this one, because it's got less carbon, it's just not going to have as much pearlite. So the rest of it has to be ferrite by default. So he heats this up, he quenches it, and he gets some increases in hardness. He goes to higher temperatures, and again, increases in hardness. Here we're up to 1525. And now we're at Rockwell 38. We see this structure is quite different. These two here are somewhat similar, but quite different from what we started with. On the right-hand side, he's all the way up to 1575, and he got a Rockwell hardness of 45. And so he stopped there, and then he added another composition, this time 0.31. So we've got 0.43, 0.13, now 0.31, repeating the experiment. Again, some things of interest. Look at the as received, the starting condition. The microstructure in the starting condition is different in each one of these because the composition is different. There's varying amounts of carbon, so there's varying amounts of pearlite. The way it's arranged is different. Again, a combination of pearlite and ferrite. And again, he goes through the heating cycle. We can see, again, really very different structures depending on what he did. And hardness continuing to increase. Here we're up to a 56. And so that's that one. Now, all of those were hypoeutectoid compositions. That is to say they're less than 0.77 or 0.80, depending on which value you want to use for eutectoid composition. He then takes a hypereutectoid composition. This one is 1.09%. And again, he goes through the same experiment. But we can see here in the as received condition, things are looking a good bit different from what we started with, because we have a lot more carbon, therefore we have more pearlite. And he heats things up. We don't initially see much change. You can see that the pearlite layers are pretty coarse here. Well, actually, this is 1000x, so they're actually pretty fine, but they look like a bit like fingerprints. And he's getting some increases in hardness as he goes up in temperature, but it's not very rapid yet. Now at 1335, he's getting quite a jump. He's up to 43. And then at 1390, he's all the way up to Rockwell 63. That's the hardness value that we've seen so far in this set of experiments. And 65, when he get heated all the way up to 1675. Remember, the first time that he did this with the 0.43 material, he heated to 1450 and was able to get Rockwell 60. Here he's at 1675, so 225 degrees hotter. He's gained 5 Rockwell points on that. This is at 1000x. We have 100x, the same structure at 100x. This is a completely different looking structure than anything that we've seen so far. So what that really tells us is that microstructure and hardness go hand in hand. And of course, hardness, we also know, is directly related to other mechanical properties. So the takeaway, one of many, is that microstructure is directly responsible for the properties that you get out of a piece of steel. So controlling the microstructure now becomes the job of the metallurgist to get the properties that the customer wants. So we're going to summarize all of his work by doing a little bit of graphing. And when we do that, we get this. So here's our carbon contents. These are the first ones. These are the hypoeutectoid steels. And we can see that he started to get transformation in all cases at this temperature. But as he went up, he had to go to higher and higher temperatures as the carbon was lower to reach a point at which he wasn't getting any further change, right? So that CD line is when if he got over that, whatever that temperature was for that composition, he wasn't going to get any further change in his microstructures or his hardness. And then we add in the hypereutectoid result that he got, and of course in his case it was just the one data point, but if you extrapolate from here out to there, you get a line a bit like that. So that you might recognize as something very similar to the iron-carbon phase diagram. And that's exactly what it is. And that's how we get an iron-carbon phase diagram. So here we have a picture of the first published iron-carbon phase diagram. This was published in 1897 by a fellow named Roberts Austin. Well, W.C. Roberts Austin is a British guy. This is the guy for whom we have austenite. It's not just a word somebody made up. It's named after a person. The same thing is true with bainite. It's named after a guy named Edgar Bain, the only U.S. metallurgist to have a structure named after him. Martensite is named after a guy that was named Martens. He's, I think he was German fella. So there's a lot of things in our industry that we take for granted terminology-wise, but they're named after people who were instrumental in developing our understanding of them. Anyway, so this fella, Austin, published the first iron-carbon phase diagram. And we can see that it's not identical at all to what we have today, but it's sort of generally there. And we're going to talk a bit more about that. This diagram, or kind of the one that we looked at that Grossman was working on, he used a technique where he heated things up and he quenched them and he looked at microstructures. But there's other ways, and he was doing that to figure out where transformations were happening. But there's other ways that you can determine that same information. There's quite a few, in fact. The first one is the microscopy method that we just described, but you could also do something like etching in a vacuum at elevated temperatures. You can use extremely precise pyrometers. You can use methods like dilatometry. These are all different techniques that will allow you to establish the precise temperature at which transformation begins and ends for a specific composition. And here, as an example, is what you would see if you were to use the dilatometric method, where you attach some sensors that will measure change in length versus temperature and plot that. And you can see that when the slope of the line changes, your specimen is no longer changing length at the same rate that it was before, and that change is due to the fact that energy is being absorbed while it's undergoing a phase transformation. So this allows you to precisely determine where that temperature is for that specific composition. We see that this particular line develops a change on heating at one temperature, and if you're at elevated temperature and you cool it down, the transformation temperature is a little bit different. That's shown down here. That's pretty normal that you would see the transformation temperatures are slightly different on heating and on cooling. So we have names for that. They come from a French word that I have put up there, but because I don't speak French, I'm not going to try and pronounce it. But we use the terms AC1, AC2, AC3 to describe those temperatures at which transformations start and end. AC1 being when it starts, AC3 being when it ends, and that's specifically for the heating condition. On cooling, you would use the term AR, 1, 2, or 3. The 1 and the 3 are the terms, the temperatures that have significance to us in industry. The AC2 is specifically the temperature at which you no longer have magnetism in the part. And so if you are reading an old blacksmithing textbook or watching somebody do a demonstration, you may see that they go to heat treat a tool, they want to make sure that they've fully austenitized it. They'll use a magnet to test when the item they're working on has lost its magnetism. That's a pretty decent gauge, but you might find that it's not exactly correct if you were able to compare to one of our more precise measuring methods. You would find that the AC2 and the AC3 are not necessarily the same temperature. For the purpose of making something in a home shop, doing something that's hand forged or whatever, it's a very good way to go, especially if you haven't learned to judge temperature by eye. So no harm in using it. But as metallurgists, it's worthwhile knowing that those two things are actually different. Yeah, Tim?
So then the AR temperatures, is AR1 when the transformation begins on cooling or when it ends?
So that would be as you're coming down, so the temperature, your transformation starts, so that'll be the AR1 would be the high temperature. The AR3 would be when it's complete on cooling, so it would be the lower temperature. Any other questions? No? Okay. So by combining all of those different techniques, researchers over the years came up with a phase diagram. This is something that we're much more used to seeing, and this is taking the work of a lot of different investigators and putting it all on the same plot. So we can see that they don't all align exactly. There's some variation in there, but they get us close. They get us pretty close. Again, keep in mind, this was published, this particular diagram was in Grossman's book, which his book was first published in 1935. So this is not new information. We, of course, have developed our analytical tools over the years. We have all kinds of equipment that didn't exist back when these guys were doing their work. And so we have a curve, a diagram that looks a lot more like this. So we've used modern techniques to validate the research from years ago, fine-tune it, tweak it a little bit, and scientists and researchers are going to continue to do that, and we'll continue to fine-tune things. But this is what we have now.
I like how the steel and the cast iron overlaps.
Yeah.
So like wood steel is really, could be considered cast iron, or it has silicon in it.
Sure. Mm-hmm. Yeah, there are, we usually, for purposes of industrial applications, most of the steels that we deal with are going to be less than 1% in general. There are exceptions, but in general, that's where they're at. On the cast iron side, I'm not sure where they typically fall in terms of carbon content.
Well, I made a graphitic ductile iron that has a 1% carbon.
Okay, so you can kind of be in a lot of different places there depending on what you want to do, which is one of the nice things about metallurgy. You have so much flexibility once you understand the relationships between the alloying elements and what they do, and not just the elements, but then the processing. It's a combination of both chemistry and processing, and it really allows for an almost infinite number of outcomes depending on what you do. So the iron-carbon phase diagram, it tells us quite a few important things. It tells us when things begin to melt. It tells us what kind of phases are present. It tells us how much of each phase is present. We can use the lever rule to get that kind of information. We can figure out the composition of the phases that are present. So it's a handy thing to have. It's important that, you know, we should really, when we say iron-carbon phase diagram, there's two things that we really should say that we don't typically say. First is we should call it the equilibrium iron-carbon phase diagram, and instead of calling it the iron-carbon phase diagram, we should really call it the iron carbide phase diagram, because that's really what's present. It's not typically just plain carbon. It's iron carbide, with the exceptions of when you can generate graphite. But that's not what we use, so you know, we have to all learn what we really mean when we use these phrases. So equilibrium, this is important. Equilibrium conditions only exist under extremely slow heating and cooling. So we'll find out later why that's significant. And then the reactions that we see in this diagram are dependent on diffusion, which requires time and temperature. So that's very important to remember. The iron-carbon phase diagram, fantastic tool, very helpful, but is dependent on these two things. So, since it doesn't tell us a few things, right? It doesn't give us any real idea about the effect of alloying elements, and it doesn't tell us the times that are needed. We just say equilibrium, but we don't really have that defined. And it doesn't really help us understand what happens when we have non-equilibrium heating or cooling. And this is quite important because this is usually what you have rather than the equilibrium conditions. So how are we going to overcome that? Equilibrium, I said, takes a long time, but really what it means is it has enough time to reach a steady state condition, or if you want to think about it from a thermodynamic standpoint, you have the lowest energy state. I said before that the iron-carbon phase diagram doesn't really help us when we start to add alloying elements, because it just captures the effects of iron and carbon. But we know that we often, probably, in fact, it'd be quite rare to not have alloying elements in steel today, right? So what happens when we do that? Well, a whole lot of things can happen. This is a diagram that gives you lots of different elements all on one thing, all together, and their effects on the eutectoid transformation temperature. So you remember what that would be for just off the iron-carbon phase diagram, what the eutectoid transformation temperature is. Nobody has any guesses? Did you guys not have to memorize this diagram at some point in your career already? You what?
We can still memorize a lot of stuff.
Really?
1333.
1333. Thank you, Dr. Metzloff. So, if that's the eutectoid temperature, what does that mean? What is the eutectoid temperature? I mean, we know what the numeric value is. What does that mean? Well, on heating, yes.
Yeah.
Yes. And on cooling, it's when austenite goes to ferrite and iron carbide. Yeah, it's the one temperature where you have a solid going to two new solids or two solids going to a single solid, right? So that's the eutectoid temperature, the eutectoid composition being about 0.77 to 0.8 carbon, right? So what we're saying here with this diagram is if we put these elements in, and you could just take any particular element and follow the line, depending on how much you put in, the eutectoid temperature is changing, right? So if I put in, let's say, 6% of nickel, and read over here, that would change my eutectoid temperature from 1333 to approximately 1200 degrees. That's a very significant change. And I can see what the effect is for nickel at up to 14, about almost 14%. And I can look at any of these other elements and see what kind of a role they would have, right? Now this diagram is not intended to show you the effect of all of these elements put in all at once all together. This is, you follow the line for a single element, and see what happens. But what we can see is that a couple of these elements, nickel and manganese in particular, tend to lower the eutectoid temperature, while most of the others raise it. So if I have both elements in combination, let's say I have nickel and chrome together, they have a counteracting effect on one another, right? Let's see some additional on this. That graph only showed you the effect of alloying elements on the eutectoid temperature. There's lots of other things that could be affected, but we see that they could have simultaneous effects, both ones that we want and ones we don't want, which may be, you could have an element that has multiple effects, some good, some not so good, so you might put that element in to get the benefits, but then have to add some other element to counteract the thing you don't want to have happen, so that in the end you get the outcome that you want. Here is, instead of the eutectoid temperature, now we're seeing the eutectoid carbon content, which we said was 0.77. But if I put in molybdenum to some particular amount, I can lower that to, in this case, like 0.15. That's a huge change, right? So again, these are not diagrams that I would think that you would memorize. These are the things that they're there for your information to help you understand the concepts. This one is quite interesting. This is specific for chrome and carbon. So if I have, what this lets us see is effective chrome content on the size of the austenite phase field. So now we're completely different parameter, not talking about eutectoid anything, just looking at where is austenite stable, right? And so I can see, that depending on how much chrome I have present, I can have a fairly narrow field in which austenite is stable, or I can make it quite broad, right? Now we're leading up to something that I think hopefully will make all this make sense here in just a minute. But keep in mind that we have chrome. You get chrome up over 12%, you're in the classification of steels that we call stainless steels. So this is very pertinent to that alloy grouping. This one is a little bit more complicated. This shows the effect of chrome, nickel, and carbon all at the same time on the area of austenite stability. So you can see here's austenite and carbide, right? So we have if you think about the iron-carbon phase diagram, you have austenite, it comes down like this, you get a eutectoid composition, it goes back up the other way. This looks completely different. The phases are the same, austenite, iron carbide, but where they're stable is completely different. And the thing to note is that there's this really narrow region right along the y-axis, right down here, where you can make austenite stable all the way down to here. We have room temperature, but if you could extend this, you could actually see that it would actually be stable to temperatures less than, at sub-zero temperatures. But you see that only works if your carbon content is low. If your carbon content goes high, you're going to find that at room temperature, you're going to have this thing going on. At elevated temperatures, you'll be up here with your austenite and iron carbide again. So this is really, really important, because this is how we get a particular class of stainless steels called the austenitic stainless steels, or the 300 series stainless steels. Those grades, we have to keep carbon low. So you typically see in grades like that where carbon is capped at, say, 0.03%. So orders of magnitude smaller than what we've talked about so far. When you do that, you can get austenite stable all the way down to even the temperatures of, say, liquid nitrogen. And so when you want to move liquid nitrogen from one place to another, you put it in a container that's made out of an austenitic stainless steel, because it stays austenitic, which is nice in that it stays tough. So if you drop the container, it's not going to shatter. We all know that if you put lots of things in liquid nitrogen and then you drop them, they shatter. That makes for some fun engineering experiments, right? But you still have to be able to move that cold stuff around. Well, you put it in a container that's made out of austenitic stainless steel. That grade or grade family maintains its toughness because it's austenite. It's austenite from, you know, liquid nitrogen temperatures all the way up to the point at which you start to melt it.
So why would it make a difference if it's austenite? What's different about austenite than, let's say, ferrite? Go all the way down to atomic level. One's FCC, one's BCC. What do we know about FCC versus BCC as far as slip planes? Or slip planes. So if you have more slip planes, and it doesn't have that ductile brittle transformation either, but
Yeah.
at low temperature, you have more chances for gliding to occur than so it behaves in a more ductile manner.
That's actually very important because brittle failure is something that is you know, a problem in a lot of situations, and that's one of the things that metallurgists are asked to get involved in, is how do we prevent brittle failure of components in service. And now you're not always able to take advantage of an austenitic structure because there's trade-offs. You know, they're not very strong, but they are very tough. So that's quite important, that idea of having ductility at low temperatures. Questions on this before we move on? Okay. So we can calculate the transformation temperatures. I showed earlier how they were experimentally derived, but that's not always very expedient, and the researchers have developed equations that we can use to figure that out. And I've put up one set of equations for the AC1 and the AC3. There are others that are available, but these are some that are common. And you can see which elements are most heavily weighted in those equations. We've got nickel is pretty significant. In fact, I would say that nickel is probably one of the most significant elements with respect to changing the start of the austenite transformation. I can take a steel that has, say, no nickel in it, and and that will have an AC1 of about 1330, right, the eutectoid composition, or it might actually be quite a bit higher than that if it's a low carbon, right? It might be more like 1400 or 1450. And if I add 3 to 3.5% nickel, I can drive that austenite, start of austenite transformation, that AC1, all the way down to, say, 1250, 1265 degrees. So, you know, a few percent nickel will change the austenite transformation and lower it by maybe 200 degrees. That is significant because when we get to our further discussions on actual heat treatment and what we do in heat treatment, that limits how hot you can go with a tempering temperature. Because if I go too hot in the temper, I'll actually start to form some austenite that can be very problematic in terms of being able to meet mechanical properties. So I have to be able to determine the AC1 so that I can carefully select the tempering temperature for those types of alloys. Here we have just a list of various types of alloys. These are the heat numbers from the mill that they came from, and the AC1, AC3, and you can see here nickel and chrome. And here's the example I was talking about. Here's a almost 3.5% nickel grade, one that has almost no nickel, and you can see the gap in temperature there. Yeah?
Can you point to those AC1 and AC3 things on the phase diagram?
Sure. I'm going to jump back several. So let's look at this one. So we don't have any temperatures here, but if you're just going to look at the lines, here's your eutectoid temperature, right? Right? And for the 0.7, this is going to be the AC1 for a plain carbon steel, no matter what the carbon content is, right? We see that. We can go along. This line is perfectly horizontal, right? That's the temperature at which we will start to get transformation.
Okay.
Now, we can change that if we go and add all these other alloying elements I'm talking about, but in a plain carbon situation, this is going to be your AC1 no matter what the carbon content is. But the AC3 will be this line here, or if you're at a hyper-eutectoid situation, it will be this line here. And so we can see that the temperature at which we are completely transformed to austenite changes significantly depending on the carbon content. So that's for this diagram, these compositions. When I start to add in the other elements, these lines get pushed up, pulled down, pushed side to side, they get bent all around, right? And that's where the calculations can be helpful in pinning down what the new AC1 and new AC3 would be for an alloyed steel.
Thanks.
Mm-hmm. Questions? Okay. Jump ahead to there. Okay. Any? Yep.
I guess I'm just a little bit confused. You said that the nickel has a lot of potential to change
Mhm.
the temperature.
Yep.
From the equations above, doesn't it seem that the other elements would have a much more of a temperature change?
Well, so they are pretty heavily weighted. You're looking at something like silicon or molybdenum, right?
Yeah.
So that's true. They get a lot of weight, but the actual amount of those elements used in most of the industrial steels is pretty low. So, for example, if we look at silicon, there's a few alloys where silicon is over 1%, but usually it's actually quite low. The same is true, like look at vanadium, that's 104, right? That's huge, but vanadium, unless you're talking about a tooling grade steel, if you're just talking about a general purpose engineering grade steel, your vanadium is going to typically be, less than, say, 0.1%. So it's pretty small. Molybdenum, you usually see that at 0.25%, maybe 0.5. But nickel, we put nickel in, and we put it in at 3% or more sometimes, because nickel has the unique, I shouldn't say unique, but certainly the significant role of improving toughness. So when you're making engineering components, toughness is quite important. It also has a significant benefit on what we call hardenability, which we will get into later in the lecture. So I'm not going to cover it right now, but it is a very necessary element in a lot of things, and so that's why I kind of picked up on that one.
And that's in degree C, the upper ones, right?
Oh, say that again?
The upper AC.
The upper one's the AC3.
No, I mean like it's in degrees Celsius.
Oh yeah, I think they're both in degrees Celsius.
Yeah.
I think.
You're modifying 9 to 10 instead of.
Yeah, those would be Celsius. Mm-hmm.
And then just a quick combination of
Mhm.
the values are inputted for each of those elements. They are in percentage or
Right. So you would take the percent that that you measure through a spectrographic test, or that is reported on the MilCert from the vendor. So those are not atomic percent; those are weight percents. When you work with composition in industry, the way that they do it, if you're making steel and you need so much percent of something, you know how much volume you have or how much weight you've got. So many tons of liquid metal, that means you need so many pounds or whatever, hundreds of pounds of this alloying element. So it's all done in weight percent, because nobody thinks in atomic percent outside of the university.
No, I was just asking more of a reference, like if it was like 0.9% rather than 0.009 or something.
Well, it depends on the element and how much is there. So sometimes you'll have something that's a very small amount, right? So I'm not sure if I understand your question exactly.
No, it's fine. I understand the answer.
Okay, all right. Not sure if I answered it right, but all right.
Yeah, that's why on the phase diagram, when you have iron carbide, it's at 6.67%. But if you look at Fe3C, it should be 25%. But because the number of moles is dependent on the weight, and carbon is such a lower mass element, it's at 6.67% by weight.
Good? Everybody clear? Okay. So we covered, let me review just very quickly. We covered the equilibrium iron-carbon phase diagram. We talked about calculating transformation temperatures, about experimentally determining transformation temperatures. Now we're going to talk about another kind of a diagram called an isothermal transformation diagram. This one is derived by a different set of experiments. So to determine this, you take your specimens, whatever you're going to deal with, you heat them up so that they're fully austenitized, and then you cool them rapidly to some temperature. That might be the temperature of just room temperature, but it could also be some very elevated temperature. So maybe you fully austenitized at 1600 degrees, and then you cool to 1500 degrees. Or whatever temperature you're interested in, and then you hold at that temperature for some length of time, whatever your interests are, and then you quench the specimen. And then you can do your metallography, you can do your hardness, and we're going to take a look at what kind of results we get when we do that. Here is just a rough idea of what could happen. This is transformation from austenite at 1300 degrees. So we know that the eutectoid composition and temperature, the eutectoid temperature would be 1330 or 1333. So we've cooled just a little bit below that, right? And now we're looking at what happens over time as we hold at that temperature, which is just a little bit below the AC, in this case we'll put the AC1, right? So initially, at the start of time, we're right up at the top, so there's been no change. But after 5 minutes, we're seeing that there's some perlite that's forming. And as we increase our hold time, we haven't changed temperature, we just increased the hold time, we see more and more and more perlite being formed until here you're out till a little over an hour. So what's been done is they heated it up to some temperature where it's fully austenitized, they cooled it rapidly to 1300, and then they held it, and then for whatever their time was that they were interested in, then they quenched it, and then they looked at the structure, right? So you can see this widely varying set of microstructures. We can see over here that if you were initially up here somewhere, fully austenitized, and you cooled, or actually here, fully austenitized here, and you cooled down to just under this line, that's what we're talking about doing, and then hold for some period of time, and then quenching, okay? We got this just vastly different set of structures. Now, let's say we take that experiment and we repeat it over and over and over again for lots of different temperatures and different times. And we plot what we get. Well, we'll get a curve like this. This particular curve is for a eutectoid steel, so a 0.77 carbon steel. And what we see is we've got, and we'll go through I know this is hard to see, so I actually sectioned this to look at individual components of it on different slides. But we can see that initially, if we cool to just below the austenitizing temperature, the AC1, and we hold and then we quench, we get soft structures and we get pearlitic structures. If we cool to lower temperatures and hold for shorter times and then quench, we get these kinds of structures here. And eventually we get down here where we're going to be forming martensites and having very hard structures. And again, like I said, we'll blow these up a little bit so you can see them better. So there's the top of that curve. And one thing to note is that this time scale is a logarithmic scale. So here we're at 1 second, and the opposite end is 1 month. And they actually did the testing out to 1 month, right? So imagine that, having a little specimen sitting in the furnace for a month. You have to wait that long to get your experimental results. I would be too impatient to do that. But they did that. And so they would do that for all these different conditions and develop these curves. And The microstructures unfortunately didn't copy over that well here, so we really want you to focus on the change in hardness, because we saw how microstructure and hardness were related earlier in the earlier experimental work, and so you can see that here. I'll point out BHN, that stands for Brinell hardness number, so that's a different, just another way of measuring hardness. The RC is the Rockwell C, probably one you're more familiar with. But you can see on the extreme right-hand side, we're at very soft hardness values, Rockwell 5. Over here, at this end of this curve, we're in the the low 40s. So quite different hardnesses. So some observations at this point. At high temperatures and long times, we would get 100% perlite. The lamellar spacing of the perlite is very coarse. We were talking about that already. And the hardness is very low. At temperatures of about 1050, so now we're back to this position here, about 1050. So this is kind of what we would call this the nose of this big curve. So when you're at the peak or the nose of the curve, at that temperature and of about 1 second, so your perlite, you still have it, but the amount is decreased quite a bit. And so we have a combination now of perlite and bainite. And we haven't really talked about bainite. Bainite is ferrite and iron carbide. The equilibrium phase diagram tells us that that's what we have to have. But the structure is quite different from perlite, and so it's able to be quite a bit harder. The remaining perlite has a very fine lamellar spacing, and then consequently we end up with a hardness of Rockwell 42. I feel like I just completely summarized what should be a very in-depth metallurgical concept. Do you have anything to add to that, Dr. Metzloff?
Well, so, yeah, basically, if you don't form 100% martensite by, remember that this is a different way of heat treating than we normally do. Typically, we're going to do a continuous cooling, or we're going to quench it in some bath. But in this case, we quench it down to a temperature and hold it. And as we get to lower and lower temperatures, what can't happen as easily? Diffusion. So diffusion you get shorter range structures. And so bainite is a short range structure of iron carbide and ferrite. As we know, things tend to form the way they do because they lower their energy, and that's what, sort of, to some extent, Mother Nature wants it to do, and it tends to do that. Perlite is the lamellar structure, and as we go finer and finer, as we go colder and colder and hold it, we get finer and finer carbides. Until what happens? Until we don't have time for diffusion to occur, right? And then what? If we don't have time for diffusion to occur, what structure do you get? Martensite. Martensite. Very good.
Mm-hmm. Good. Thank you.
What is bainite?
What is it?
Yeah. Like, it's different from cementite. Has the same.
Well, so cementite
Not
is
cementite, perlite.
right.
Perlite.
Yep.
But what is the different shape? Is perlite eutectic? Then what is bainite kind of?
So perlite's lamellar. Bainite can have different forms depending on the temperature at which it is formed.
Okay.
I don't have any really excellent images of just bainite, but you could certainly go and find some. What you often see is that bainite is sometimes described as having a feathery appearance,
Okay.
where perlite is lamellar. Some bainites have this kind of feathery look to them. That's not, and we categorize bainite into upper and lower bainite depending on what temperature it formed at. So the upper bainites tend to be the softer, more coarse-looking bainites, and the lower bainites are harder. Bainites can be very tough, but they can also be very detrimental and cause a lot of loss in toughness. When you have bainite where it's just a small amount of bainite that's say embedded in a matrix of perlite, or perlite and blocky ferrite, that bainite will be the hardest constituent in there, but if it's sort of isolated all by itself, that hard spot's going to serve as a crack initiation site. And so that's a problem. But on the other hand, if you have a uniform bainite structure, you can have an extremely tough item, whatever it is that you're making. So it really, as with everything in metallurgy, it really depends on what you're trying to accomplish and what you're able to accomplish given the chemistry and cooling resources you have available.
One of the things, they have another word for it, like Fisher Barton, one of the companies that they make all the lawnmower blades pretty much for John Deere, all the higher end ones. And they find they can get a slightly higher hardness for the same toughness in around the 40, because remember, a lawnmower blade can hit a rock. So if it hits a rock, it can't shatter and kill people. So, but the problem is if they use tempered martensite, it doesn't wear as long. They want it slightly harder, so they find they can get that in bainite. So they can get the toughness they want and a couple points higher on the hardness, which makes the wear resistance go up. They call that Ostempering. So that heat treatment they do it has a, but all it is, it's a process whereby we do something off the IT curve.
Mm-hmm.
So.
And we'll actually get to that a little bit later as we break down this curve more, and you'll see how you could accomplish that in a very intentional way. So here's the next segment of our curve. Remember, the nose of our curve was at about 1050, so now we're below that, and we're seeing that the curve is coming back this way in the time. So from 1,000 degrees down to about 600, we see that we have more perlite. We are decreasing the amount of perlite and replacing it with bainite that we were just talking about. The bainite that we formed at high temperatures and low temperatures have different structures and different hardnesses. You can see that represented somewhat in these images. Like I said, those are not the best images to show that. But we do see that we get an increase in hardness from 42 to Rockwell 50 as you have more bainite and the lower bainite being formed.
So we have in this particular alloy, which is plain carbon steel, at 0.8% carbon, we have 1 second to get it from its austenitizing temperature past
That
the lower temperature
that was, well, 1050 was the nose of the curve for this alloy is 1050. So yeah, that's extremely important. If you're trying to make something that's free of perlite in this particular composition, you have to cool it past at least 1050 in 1 second. Which means your specimens have to be very small, or you have to have some very large cooling capacity, or some combination thereof. Now, if you can get it below that temperature, let's say you can get it down here to 700 degrees, well, now you'd be able to hold it for 10 seconds or something like that. You've got more flexibility. And you'll see that as you go to lower temperatures, you've got more and more time. So that gives you this ability to, if I can initially quench rapidly, then I can slow down my quench here and find some temperature that I might want to hold at for a while to allow some structure to form, in particular this bainite that we were just talking about. And this is how we do the Ostempering that Dr. Metzloff mentioned, is you get it rapidly cooled, but you don't cool all the way down to the temperature you need to form martensite. You cool to some intermediate temperature that gives you all bainite or a combination of bainite and some other structure, whatever it is that you want. You allow that to be maintained at that temperature till you have that transformation complete, and then you cool to room temperature. Usually that's accomplished by quenching into molten salt. You can get salts of different compositions and that have different melting temperatures. So it's relatively easy to have very uniform temperature control at very precise temperatures, and so it allows you to really dial in your process for the alloy and the outcome that you want. Now, if we look at some more here, we're almost down to the end of this curve. We see that it starts to sweep back out this way, coming back towards the left. We're down here to 200 degrees. At 420 degrees, kind of right in the middle of where I'm at, we see that the start of transformation, we were sloping to the right. Now it starts to slope back to the left, and we see a big increase in hardness if you look at the hardnesses that are over there. That's where you're starting to get martensite being formed. So if you want martensite, you can see that you would have to cool initially rapidly. You could slow things down for a while, and then you'd have to speed it up again to make sure you don't form, if you're trying to get all martensite, that you get all the martensite that you want. So you can do that. Sometimes you do that just by doing a straight quench, where you just cool the item as fast as you can and get it all the way cooled down, and then you temper it and you get your tempered martensitic structures. But you might do more of the aus-tempering kind of situation, not necessarily with the goal of forming bainite. You might be trying to form martensite, but you might be trying to prevent, say, cracking in a part. And if you've got a part that is a large component and it has a big delta T between the surface and the center, you might do something like the aus-tempering type of approach to allow the part to become to a more uniform temperature at some intermediate spot, and then finish the cooling. We do this on occasion in the big forgings that we make, because otherwise we would have significant risk that they would crack.
Just to be clear, you're really not forming any martensite until you go as far down the graph here, correct?
Here?
Yeah. There's a line there?
There is a line. There's one more here. If we jump here, that's the very end of it. This particular one, I think you would actually start to form martensite
at horizontal, angle line is right there.
This one here?
No, that one.
Here?
Yeah.
Yeah, right here. You see it says transformation begins?
Yeah, that's actual martensite.
Yeah, right. For this alloy, that would be at about 400 degrees.
Right.
Yeah. Mm-hmm. Yep. And then the very end of it is here, and you can see if you do quench super rapidly and you can get everything cooled down, you can get out of this alloy, you could get a Rockwell hardness of 66. So pretty high hardness material. So the value of this curve and is not that we use isothermal in practice. That's not what we normally do. It is going to be more through a continuous cooling process, which we'll get to in a moment. But what it helps us understand is what happens when we have holds, or maybe I should say delays, at various temperatures. If you, let's say for example, you are trying to get something quenched and you have to move it some distance, or your material handling device breaks and so you're stuck. Well, you have a limited amount of time to get your item from the furnace to the quenched device. And if you don't, and the part sits out in the air, you're going to start to undergo something more like what's happening on this isothermal diagram, and you'll be able to see what that would be. So this helps us understand why, when we're in practice doing practical heat treatment, we have to pay attention to how fast it takes us to get something from our furnace to our quench tank. It's not unusual to see in industry where customers will mandate that the transfer times be capped at some maximum. So 60 seconds, 45 seconds. In certain cases, for certain materials, not for steel, but for aluminum, in many cases, that's capped at 10 seconds. You've got to go from your heating furnace to your quench in 10 seconds or less. Now, I'm not familiar with how aluminum, whether that has isothermal transformation diagrams and behaviors like steel, but I do know that if you don't get it fast enough, you're not going to get the outcomes that you want. So in industrial practice, the way they make that happen, because you can't move a large item with a forklift fast enough to meet that requirement, they actually build the furnaces over a pit, and the pit is filled with the quench media, and they can just, the bottom of the furnace can just be lowered straight down into the quench bath, and that's how they satisfy that requirement. They call those drop bottom furnaces. Questions before we move on? Nope. Okay. So this is another TTT diagram, a little bit more simple. we see here that we don't get martensite over 420. Here it's delineated a little bit more clearly because we don't have the hardness and the microstructure shown on there. But you can really see here how fast you have to cool to miss the nose of that curve, how important that is. And you can see how you have kind of a, you could call it a bay or an open spot in here that gives you some flexibility. So we're going to talk about, again, this was the eutectoid composition, but we don't use the eutectoid composition for everything, right? That's just an example. What happens in real life when you want to make something out of something else? Here's a different one. This one, we have a combination of TTT diagrams for different compositions all laid on the same scale, right? So here we have one. This one is a 0.5% nickel with 0.6 carbon. Over here we have one that has almost 4% manganese and 0.55 carbon. We can see others up there. The thing that's important to notice on this is that the nose of these curves is all over. Some of them are very, very close to the left-hand side, which means you have very short times to deal with if you want to try to miss those transformations. Others, like this one over here, goodness, I've got, you know, I mean, 1,000 seconds? 1,000 seconds, so I can take my time to get that one to the quench tank. Or in certain cases, I might have, it might be pushed so far to the right that I don't have to take it to a quench tank at all. I can just let it cool under ambient conditions and I will miss the nose of that curve. Those are specialty alloys, but there's some out there that are like that. Here's a more common grade. This one is 4340. So this is a, you can see the composition there, so it's got quite a few different things in it. We can see we have multiple curves here. What these are showing you are where you start and kind of finish the different, getting the different phases. So usually you'll see these curves represented with an initial line that shows you when transformations initially start, where your 50% transformation line would be, and then where your 100% transformation line would be. And you kind of can see that up at the top of this graph where you've got the three C-shaped curves laying right next to one another. They've got some extra information on this one. But that's for a 4340. Let's take a look at another grade. Whoops, not yet. We're going to practical application. I do have some more TTT's diagrams to show you in a minute. But application, heat treatment for engineering applications, almost never done under equilibrium conditions. So the phase diagram becomes a starting point, a foundation for us, but I almost never look at a equilibrium phase diagram when I'm trying to solve a problem at work. I may, however, look at a TTT diagram. Due to variations in size, only the smallest parts cool uniformly through the cross section. So I didn't show, you know, I didn't prove this to you yet with a simulation or data off of embedded thermocouples, but I think it's pretty intuitive. If I give you a part and it's 12 inches in diameter and I give you a part that's 1 inch in diameter, they will cool at different rates. And so even if they are the same composition, they're going to be cooling differently. Therefore, you're likely going to potentially hit the nose of that curve for that alloy. So again, in the practical side, we have to pay attention to sizes. All right. That brings us up to a thing called a CCT diagram, which Dr. Metzloff mentioned. However, it is also 4 o'clock. I think this is probably a good point to stop, and we'll cover the rest of the material in 2 weeks, unless you guys want to do something different.
Okay, some builds to and some.
Yeah, we've got some fun stuff to do in the lab tonight. Are there any questions about these concepts? I know these are a bit more heavily dependent on your understanding of physical metallurgy, on diffusion, on phase transformations, things like that, and I didn't dive super deep into all those, so I want to make sure that you're comfortable with the concepts. Everybody's pretty good? Okay. Well, if you think of questions about this stuff while we're in the lab, please ask.
Okay, so I think the plan would be to
ladder pattern Damascus dagger from some steel that we welded and forged earlier in the evening. This is Material Science 401 lab class. The materials in the dagger, in the blade here, are some industrial bandsaw blades and some nickel shim stock. The bandsaw blade seems to have a composition somewhat similar to S7 tool steel. The first step is going to be to forge a tang. This will be for a hidden tang style knife. The ladder pattern has been ground into the billet, and after the tang is forged, I'll forge the billet flat and then forge it to a blade with the bevels in it. We'll be using this tool to create the shoulders. You can see here that the tool has a bevel which I can use to create a fairly sharp shoulder on one side, a bevel on the other, and then I can draw out that bevel into a smaller dimension. That is the result. Now we're going to start drawing out the tang. What I did, you saw me grind those grooves into the filling. The filling has laminates that are straight, okay? And when you grind through and then flatten them, you reveal kind of a straight pattern. That's what I'm showing you there. Mine's probably not going to be quite as visually stunning as that because there's not as many layers in the filling. But it's still going to be interesting. You can see even without much going on yet, you can see the stripes in here. The nickel stays bright even with the oxidation from these high temperatures, and so you can still see it.
obviously, that when you make those ladders in there, that you don't make them so deep that they'll fold over.
The other thing that I did is I staggered them one side to the other so that when I flatten them, they'll kind of move like an accordion a little bit. It's not so deep, it's and that and a whole separate technique. They'll get a little longer.
Did you turn that video on here?
I did turn it on, yeah.
Okay, good. I'm gonna, can I turn your handle?
Sure. Trying to work this fairly hot because we have a laminated construction here. It's doing pretty good. It's doing pretty good, but
You get different thermal expansion coefficients and all kinds of stuff, wanting to make it move harder.
this is definitely harder material to move than 5160 that we used for the last project.
Is that because of the nickels?
Well, the nickel and the chrome. There's actually not so much the nickel in the billet. Because nickel all by itself is actually fairly soft. Steel has 3% chrome, 2% molybdenum, a little bit of vanadium in there. So, and then whatever carbon content it has that I couldn't verify today. So it's an alloy that's, quite expensive. Yeah, so the big bandsaw blades, if they're carbide tipped, they'll cost $500 a piece. We go through that stuff like, yeah, exactly. It's just a consumable in the shop. It was running a little hotter, it was a little smaller, so yeah, it's working a little bit better. We'll see how it does when I spin it around and start to draw out the blade. I have to work the dagger a long time. But I think it'll actually look pretty neat. Yeah, we had to stack it out. It didn't warp that bad though. I mean, after it calmed down, it cooled down. It seemed like it.
Yeah, but you should have this side.
That happens before.
Yeah.
They get hot and they change shape.
Slide them down that thing, they have to have a square hole in it. Or you can make a round tank. And you can slide them down the tank. And then on the end piece, on both sides, the sandwiches it, right? One of them goes up against the back of the blade itself. What's it called? The front end?
Console?
Yeah. And then in the back end, you have another cap, what's that called?
Hollow.
And then what you can do is, if you make it narrow at the end and round, you can thread the end. And then what it does is all those layers, you put them in compression. And then you go and you sand the thing however you want, and it makes a pretty cool, layer kind of thing. So that's one way.
The daggers I made for my daughter when I brought her to first day classes.
Yeah. And then you can make the one I was talking about before, where it's completely enclosed. That's the hardest thing to do. I use epoxy. I don't know what other people do. But
This style here can be done either way. I can make it long enough that it comes out. You not only you thread the end, but you actually clean open the end too. Ribbon place, that's how you're sorted. Or you can just drill a black hole in your hand material and epoxy it in place and shape it the way you want.
So just curious, if you were to like paint the end over, how would you go about that? I mean, you're basically upsetting the material. What do you?
So you have to support the end.
clamp the knife in a vice or
Vice or on something that's hard but not marring, so it wouldn't block or something like that.
Yeah.
And you might even take a small torch and heat that piece of PE.
Okay, that's what I was thinking.
It's little
Just to-
too, so it's just like a plain ribbon good.
Yeah, yeah.
The nut that you put on the back, what you normally do is you cover board. The nut looks like it's like a round nut. I have one I put in here, it's a round nut. That was a spot on the top, but it has to screw it down. Eventually, the rod comes up and gets in the way. So you have a screwdriver that notch that goes around that. That's the so that's my goal to make it.
Yeah, I've watched a lot of making that. I want to make the like the survival line, so you'd have the handle, make the handle itself, metal, then you kind of machine out the inside with a lighter and kind of repair it.
Yeah, people like those. The challenge is how do you attach the blade, the handle, and have a good handle, right? Not impossible.
One piece.
Yeah, one piece.
Oh, well, then, yeah, you can certainly do that, have it all there, yeah. Those are kind of hefty, they're every time, but yeah. I can do that for sure.
Yeah, the sharp defense weapon was this one solid piece of stainless with the holes in it where the handle is, and it pinches out a little bit. It's a double edge.
Was that something you made or something big?
I just bought it for cheapo. It's in my luggage, so if it gets stolen, I don't want it to be something that we care about.
Right?
Didn't have to use it, so that's good.
Well, that is good. Remember really what happened?
It's a lot of shards, but I didn't have to use it.
Saw a lot of sharks. Did you swim with the sharks or? Yeah.
Well, I mean, you're there. You're in their neighborhood.
I suppose that's true. Not sure how I would feel about swimming with them.
We call it wildlife.
Right?
For
Well, yeah. That's where we went surfing. We keep on catching the same fish. They can't kill them. There's a lot of shark hookers. I went surf right there.
That's about 10 foot long, 8 foot long, something like that. I get up to big light out there.
Oh, yeah.
This is pretty cool. So it's like a ratcheting, some sort of ratcheting gearbox.
Okay. So there's the tank, it's not perfect, but a lot of stuff for file, and all that. But it's long enough, got really safer to it. Now let's do the blade. So the thing that I'm gonna do on the blade, we first to flatten out all those grooves, and then draw them to a point to make it uniform, make a point.
It's fabulous. It's, you guys have me. Dave earns 3,000 pounds a month, spends 750 pounds a month on car repairs. What does Dave have? A Land Rover. Dave has a Land Rover. It's like one of those kids' problems.
Yeah, you find that you guys did much repair work?
They're kind of known for that. They're pretty indestructible. The deal is that if something breaks on them, they're so like mechanical that you can wire it together and get out of Botswana or wherever you are. If your Toyota Land Cruiser's electronic module, fuel injection module, or some shit like that goes, sorry. The only thing if the Bosch fuel injectors go like, well, I have extra injectors. Yeah, I have injectors, but the mechanical fuel injectors, they last for like 300,000, 400,000 K. So they're not likely to go. So the problem is that like it's getting hard to find people who want to fix the old stuff. No one fixes anything anymore. Oh, I just put it electronic. Oh yeah, the computer says that I need to replace this module. That'll be $1,200, please. All right, might be unplug this. Fuel supply, so turn this switch on. That's cool. How it's flat now.
I had a 1999 Firebird and a fuel pump one. And for those cars, the gas tank was located above the rear axle. So we have a choice of the distance we were in the car, drop the drivetrain, drop the rear axle, drop the gas tank, replace the fuel pump. Or you just cut a hole in the back, right above, like if it's just thin gauge steel.
All right.
You just cut one single hole right above the fuel pump.
Yeah.
You just swell it back up then, or?
No, you don't even need to because it's not a structural part. I mean, it is a body part. No, I mean, at that point it's just so high above the tank.
Oh, it's up. It doesn't get.
How do we get up to the front?
So it's right behind the rear seats. Between, so I had a Firebird with T-tops, so it was like my trunk and hatchback basically. It was like right, it's just a basically solid metal box right over your gas tank and axle. So you just build the carpet, cut a hole, place the fuel pump, go back in. And that was about an hour and a half fix instead of
Oh, the other one.
days.
Yeah, wow. have a name. Some people call it a check pattern hammer. I think the guy who made it calls it a teapot style hammer. Some would call it a rounding hammer. And that this side is round, this side is square. The fellow that makes these makes them in a smaller size. I saw some at the Blackfoot meeting I was at a couple weeks ago. He had them like 2 or 2.5 pounds. There's lots of hammers available. You know, that one was imported. I got what I by that particular maker. I got others that are handmade. But $5 like a hammer will work just in time to rest that face and make the hammer something that you're comfortable with. This one I asked it for because I was using I was one second effort for certain operations I was doing. So we used to make this one similar to what we did before. Don't put my hands like that. Buy a hammer, look at that 2 hammers. For a handmade item, it's fun. Yeah. It's a great to work. Great nice. But if you start out, I'm not really starting to finish on the hammer. I switch that, but I always look for something more. There's lining up everything. Still not all the way up, so I have to leave that. So we were talking before about taking a single edge blade and having it want to sweep off and waste the time after that. This is going to be a double edge blade, so we're good, right? Let's stay there. I should be talking to the camera, but it's over there, you know, it's kind of right now, I'm just going to kind of true up the profile a bit. It's not a real thick knife still. The metal's not going to be, you know, it's not going to get a lot of weight. It'll be a little bit thick. That's it, fine. I'd like to work over here and get off the edge of the anvil, but that's going to be a bit tricky. The anvil kind of looks like that. Then when you go with the crew break? Well, hanging around. We're going to Texas tomorrow. We're what? Texas. Texas tomorrow. Is that home? South, Philly, What part of Texas? Austin. Okay? Yeah. what happens. Something that will closer to a star pattern. I have to try to work out here a little bit. I don't know if you guys can see the pattern when it comes out of the furnace on the surface. A little bit. I can see it over here because the nickel oxidizes differently, even though they're both very hot. You can still see where the two materials have a different appearance.
Surprisingly clear.
Yeah, actually, this temperature is even easier to see it down. Now, if we take this and we get it shiny, and then we bring it back and run the flame into a temporary kind of operation, we get a blade with like color to strip there, the nickel will stay silver, so it will be blue or silver streak. You know what that is? 440?
Yeah.
Which one?
What?
Which
Oh,
one?
that's a good question. I'll be back on that.
Get a nice sharp ridge line down the center. That's kind of what I'm shooting for. I'm not sure if I'll be able to do that with the working tools.
It just really cut me out every time that works outside, but it screams up the other side.
Yeah. Yeah, well, stretch it all out on one side. Not quite even on this side here, so we'll try to pull that out a little bit more.
How we doing? Good, yes.
Coming along. Yeah, awesome.
140C.
40C, all right. You make that out of it.
size and ring thickness right now. But I want to straighten it and flatten it a bit. It's a little messed up.
Is that something you guys rolled here?
Yeah, actually, it used to be twice this thickness, and then I alligated it. I think it was a combination of, it was originally each bar, so I think the production was too high and didn't round off any of the corners. So, as you can kind of see, I think it lapped itself about here, and then that lap propagated and cracked.
Yeah, that can happen sometimes.
How thin do you generally take a blade down? Especially like around the pit.
Depends on what I'm doing. I would probably take blade for lab rocket. I'd probably take this down cutting edge.
Yeah.
Before you don't want to have so much driving out to do to overheat like
Think it's gonna work?
Yeah?
Yeah. It's just a little aggressive on a couple spots. Back on the side, otherwise it looks pretty solid. Good stuff.
hit that hose.
Yeah, no, I just straightened it a little bit, but it's actually sparking a little bit.
Well, we're going to see the 1% carbon steel, so 1% carbon and 4% something like that.
Is it possible that I hurt it?
I don't think so, no. Yeah, I think I'm going to consider the way that there's a company in there that I can do some writing. I don't know if I'll get a strong center ridge. I might. But it's a little bit, well, I'm not sure. So, let me see. It's got a little bit of a profile to it, so I'll need to write that belt writers or whatever. If I can borrow. That's what I'm trying to study that.
Oh, hey, how's it going?